Okay, so finally we're going to talk about the enthalpy, and so here the illustration is actually a historical experiment of that involves steady flow of a thermally insulated system, and this is something that was done by Joule. So remember, in the very beginning we have said that Joule he wanted to establish what was the temperature dependence of what was the functional dependence of the internal energy in an ideal gas, and there was this experiment that we analyzed of the Joule expansion. Okay, so by that experiment, Joule had experimentally established that the internal energy of an ideal gas was solely a function of temperature and not of volume, but he must have not been very convinced by his experimental setup or by his experimental precision in determining the temperature changes in the calorimeter, because he made a further experiment to independently establish the same fact that the internal energy is only a function of temperature. Okay, so what is it that he do? He did experimental setup that was implementing theory that was developed by William Thomson. Now, William Thomson is Lord Kelvin, so his real name is William Thomson, but he was Lord and First Baron of Kelvin. That was his title. And sometimes in thermodynamics we use the name Kelvin, for instance, the Kelvin temperature scale, and sometimes we don't. But I think I already might have said this in the beginning, but I don't remember. Anyway, so this William Thomson is Kelvin. And the experiment is like this, okay? So you have a tube that was what Joule used was a tube made of some birch wood, which is a very good thermal insulator, natural thermal insulator. So approximately you can consider that these walls here that I'm drawing are actually adiabatic, okay? So as usual, let me just make them thick like this. And there is some gas inside, so it's a gas that is at very low pressure, it's very rarefied, so to very good approximation it should work as an ideal gas. And there is a pump somewhere that is moving this gas around, but what I assume is that I have waited long enough so that a steady flow has been established. So the state of this system, if I look anywhere in the pipe, I see that all measurable quantities are independent of time. I'm already in steady state, so I'm in steady state flow. And imagine here I interrupt the flow by putting some obstacle. And this, in the case of Joule, this was a piece of cotton wool that he put here. Okay, so it's a porous obstacle. This experiment is sometimes called the porous plug experiment, or the Joule-Kelvin experiment, or the Joule-Thomson experiment, or the throttling experiment. So it's different. It has different names, but it's always the same thing. So okay, there is the obstacle, but of course the gas can flow through this obstacle, but as a result of the obstacle there might be different pressure on the two sides of this obstacle here. And like I say, I wait after I initiate my process, I wait long enough so that the system is already in a stationary situation. Okay, so then we have to make a thermodynamic analysis of this situation, and imagine that you make a division, but this is completely imaginary division for us to work, and you single out a small parcel of gas to the left of the obstacle, and this parcel has certain volume, and the gas inside of it, and let's call it volume 1, the gas inside of it has certain internal energy, U1. Okay, and there is a certain mass of gas there, which we call M. Okay, so if we normalize everything by the mass, so we define the specific volume, let's call it lowercase v, is the total volume divided by the mass, and the specific energy is the total energy divided by the mass. Okay, so imagine the mass is 1 unit, 1 gram or whatever, and from now on we forget about the mass and we always work in specific variables. Okay, so fine. Then let's do it already. So we have specific volume V1 and we have specific internal energy U1. And we are going to follow this parcel of gas as it moves through the obstacle and emerges on the other side, okay, on the right hand side. So if I somehow kind of trace every single bit of gas to the left of the plug as it goes through the obstacle and to the other side, I would see that in the end it will occupy generally a different volume. It's the same amount of mass, but the specific volume, or the volume it occupies, is going to be different, so the specific volume is also different, and the energy is going to change in principle, okay? So in such process, if you write the first law of thermodynamics, and we are following this parcel of gas, so we say, what's the change in the internal energy of the parcel of gas, which is U2 minus U1? Well, there will be some heat, but actually there's no heat because I said that the walls of this tube are thermally insulated, so there's no heat. Let's say heat 0, and there will be some work per unit mass that is made on my parcel of gas. So all the energy change is due to work, and this work is something we can calculate, okay? So let's try to have a go at this. First of all, consider that this system that we are delimiting here is being pushed by the gas that comes after it, okay? And this gas that comes after is pushing until all the gas goes through the obstacle. And this means some work is being done on the system. And how much work is that? Well, that's minus pressure, and then dV, where this is specific volume, and the specific volume starts being V1 but ends up being 0, okay? And this is, if you like, work 1. And what this is nothing but P delta, or well, not delta, PV. Okay, that's the result of it. So that's the work that the gas that goes after is doing by pushing your system through the plug. But of course, when the parcel of gas emerges on the other side, it has to push whatever gas was sitting here before to make space to be on the right hand side. So your system is also doing some work on the outside, and this work is just going to be simply minus P V1. Okay, sorry, V2, because it has to push all the way until it occupies the entire volume available to it, which is V2. Okay, so then we can write that U2 minus U1, which is simply delta U that we saw before, equals W1, well, let's just write it what it is. So it is PV1 minus PV2, which is W2. Okay, and we can rearrange this, and we can write actually U1 plus PV1 equals U2 plus PV2. Or in other words, the specific enthalpy on the left hand side of the obstacle is the same that it is on the right hand side of the obstacle. So when you have stationary flow in a thermally insulated thermodynamic system, the enthalpy is going to remain constant. Okay, so this stationary flow is an isenthalpic process. And remember, we did refer to this when we were in the self-study pack on the finite time thermodynamics, when looking at thermal power stations, well, nuclear power stations in this case, there was a mention to the enthalpy as to how to calculate heat absorbed. So if you just see that the flow is steady, but the enthalpy changes from place to place, that must be because there's some heat going into the system or going out of the system. That's why. So fine, we just have established that when you have stationary flow in a perfectly insulated stationary flow in a perfectly insulated system, your enthalpy doesn't change. And okay, so this is what we know from theory, but actually Joule, in his experimental setup, he was also interested in having a thermometer here on the left hand side, and also a thermometer here on the right hand side. Okay, and he measured the temperature difference in the two places, and also he measured the pressure, P1 and P2. And what they saw is that the pressure did change on the two sides, as you could expect, but the temperature was exactly the same. Okay, so what this means, if you want to express this as a derivative, is that the temperature does not change even if the pressure changes in an isenthalpic process. So this derivative is zero. That's what Joule arrived to. So this is the conclusion that you arrived to from measuring the temperature on the two sides. Because you know, what's the change in temperature when in an isenthalpic process, which is steady flow, thermally insulated, when the pressure changes by some amount. What is this? In the limit, in the infinitesimal limit. But this is zero. This is what Joule was finding. And okay, this is one of these nice derivatives that we can now reduce using the tools and techniques that we have learned in this chapter. And in particular, you could use this trick of the mixed partial derivatives, like T, P, H. This cyclic trick, which is then P, H, T times H with respect to T at constant P. This is equal to -1, which means that this derivative that we are interested in is simply minus, and here you have partial of H with respect to P at constant T, and here is a partial of H with respect to T at P constant. Okay, and this Joule established that was zero. If such a thing is zero, then this thing in the numerator has to be zero. Okay, so what follows from the porous plug experiment carried out by Joule is that the partial derivative of the enthalpy with respect to pressure at constant temperature is zero. Okay, so now imagine the enthalpy is expressed in terms of pressure and temperature. Okay, you know, these are not its natural variables. This is something we do know, because the other natural variable of the enthalpy is the entropy, but we don't care. We just choose these two variables for convenience. And if we were to express the differential of the enthalpy in these variables by the chain rule, like you know, this is going to be this plus the partial of that with respect to P at constant T differential of P. Okay, and Joule established experimentally that this derivative is zero. Okay, which means that the enthalpy for an ideal gas, and this derivative, and so I emphasize this because I didn't emphasize this enough, this is what Joule found in his experiment, that he was working with an ideal gas. This is not true in general, and the whole of the next chapter is going to be devoted to the fact that this is not generally true, and you can actually exploit the fact that this is not going to be equal to zero. But for an ideal gas, the enthalpy is exclusively a function of temperature. But the enthalpy, remember what it is, right? It's the internal energy and then plus PV. And PV for an ideal gas is nRT. So if H is a function of temperature, then necessarily U must be a function of temperature only, because the next term I have here is also a function of temperature only, right? So there's no volume, there's no pressure. So this is an even more conclusive proof in experiment that the internal energy of an ideal gas is just a function of temperature. We don't need this proof because we know that we can show this by the properties of the entropy, like we did in the previous chapter, but back in the day Joule didn't know that, so he repeated his experiment to be completely sure. So that concludes this chapter, and in the next chapter we are going to, like I say, see practical consequences of the fact that in a real gas this derivative is actually not zero, and this can be exploited to cool and liquefy gases. Okay, so I will see you in the next lecture.